Hello, Ross. Let's talk about lesson 1.10 on solving quadratic equations. At the grade 11 level, again, we expect efficiency here. We've sometimes had students that try to use the quadratic formula to solve all quadratic equations, and that's not always the best option and can cause some problems. The other expectation is outside of applications, we will always expect students to give exact values in simplest form. That shouldn't have to be asked. But because we have experience in other courses where all we need is a decimal approximation, you will be reminded when you're looking for exact values in simplest form. Okay, so the first example I want to look at is an example where I see a lot of students struggle because they don't see this as being quadratic. I want to show you some of the most common mistakes that students make. Students sometimes try to solve by isolating for x, and that's difficult when there's two instances of x. Students end up dividing by an unknown, which is a bad idea. And then they end up only getting one solution to a quadratic equation that I'm pretty sure can often have two solutions. The other thing that they don't notice is I think one solution should be visible here. What's a square of a number times 6 times a number, or plus 6 times a number to equal 0? 0 squared plus 6 times 0 is 0. And I just divided by x, which could have been 0. So this is not a great approach. In class, I show how to solve quadratic equations by isolating, and it involves completing the square. So we'll try out that approach in a sec. But yeah, if you want to think about this as a curve, like there is no quadratic here, but if we introduced a function, f of x equals x squared plus 6x, wouldn't we be within reach to get it into factored form? Can't we just see that it's going to have 2x intercepts? Solving by factoring then, when you can solve by factoring, it is very, very fast. So let's say try factoring first. It might take a while to figure out if something can be factored, and sometimes it's going to be faster to just use the quadratic formula than to try to figure out that something can or can't be factored. But if the numbers are small, if they're integers, if they're reasonable, and if you've practiced factoring, then it's going to be worth it. Because if I can rewrite this x squared plus 6x as a product, and then say, well, either x is going to equal 0 or x plus 6 is going to equal 0, and that means that x is either 0 or negative 6, I can have the solution in seconds. Like with our conversations around the axis of symmetry, I feel that a student that uses the quadratic formula to say x is going to be negative 6 plus or minus the square root of 6 squared minus 4 times 1 times 0 all over 2 times 1 is demonstrating, not that they have mastered the quadratic formula, but is demonstrating, basically this is saying, I don't know how to common factor. So I don't believe it should result in the same mark. I mean, it should give me the same answers, but it's not too hard to see that this is taking me a little bit longer here. Let's see, negative 6 plus 6 would be 0 divided by 2, or x is going to be negative 6 minus 6 would be negative 12 divided by 2. It means that x is going to be equal to 0, or x is going to be equal to negative 6. I've said this a number of times in our course. The purpose of this question isn't to see if you can find the answers. Like, I don't really care. I'm not interested in what the answers are. I'm interested in seeing a well-communicated and efficient solution. And this approach is inefficient. If I resort to the quadratic formula every time I'm asked to solve, of course I'm going to run out of time on quizzes and tests because I shouldn't be using this inefficient tool. Like I said, it also demonstrates a lack of understanding. Demonstrates a lack of understanding of, I would say, binomials and common factoring. Okay. Let's try another question. Let's solve when is 18x squared minus 9x minus 2 equal to 0. And because of the fact that my a value is larger than my b value, solving by completing the square isn't going to be a great approach. I could show you this one solving by completing the square, but I don't think it's an efficient approach either. We might have some concerns here because we're not entirely sure that it can be factored. I scan for common factors and I see the number 18 and I realize that there's a lot of combinations there. Well, a couple, I guess. By a lot, I guess I mean 3 combinations, but 2's a prime number. So if this does factor with integers, I think it's going to be worth the time that it'll take to check this. And this is what I like about the the cross method, is because it will exhaust itself. If it turns out this can't be factored and I have to use, let's say have to use the quadratic formula, I'll know when this can't be factored. I'm multiplying diagonally, looking for a target of -6. I get 6 and, or sorry, -9, 6 and 6 won't do it. 12 and 3. Oh, look at that. That didn't take too long. I might have gotten lucky, but I also have suggested keeping, like checking the 6 and the 3 first. -12 plus 3, so let's do a -2 plus a 1. So I'm going to write this in a factored form as 6x plus 1 times 3x minus 2 equals 0. That means that 6x plus 1 is equal to 0, or 3x minus 2 is equal to 0, which means that 6x is equal to -1, or 3x is equal to +2, which means that x is equal to -1/6, or x is equal to 2/3. So that wasn't too bad. Let's compare this to the quadratic formula. The quadratic formula here would say that the roots of this quadratic equation are the opposite of -9 plus or minus the square root of -9 squared minus 4 times 18 times -2 all over 2 times 18. What often happens here is a miscalculation that students won't catch, that I don't think would have been an issue if they made their numbers smaller first by factoring. Here, x equals 9 plus or minus, let's see, the square root of that's going to be 81 minus 9, 18, 27, 36, 45, 54. Did I do that right? 18 times 2 is 36, times 2 is 72. Did not do that right. Times 2 is 144. I might want to check that with a calculator. Let me just do so quickly. 9 square, sorry, 4 times 18 times 2. There we go, 144. Yeah. So there's a disadvantage. I didn't have to reach for a calculator for this, but I kind of was nervous about multiplying there. I'll squeeze over here. This means that x is equal to 9 plus or minus the square root of, 225. All over 36. And the way you'll know that the function, or the expression could have been factored, is when you get a perfect square radicand. So I recognize 225 as being a perfect square. That is the square of not 25, 15. 6 25s. It's 36. I guess I would split this up and do x equals 9 plus 15 is 25, 24, 36, or 9 minus 15. Let's see, 15 minus 10 is 5. 6 minus 6, 36. And here's the disadvantage of making my numbers bigger. I now have to make them smaller. Let's see, I'm seeing a shared factor of 12, so I get x equals 2/3. Or I'm seeing a shared factor of 6, so -1/6. Again, I will argue politely with any student that says, I think this is easier. Okay. I think not learning how to factor is easier than learning how to factor, but I would say this is easier and more efficient of an approach in this case. Right. If you want to see me complete the square to solve this one, ask me outside of class time. I don't think it's a great approach. Let's try one more. Well, maybe 2 more. Let's solve when is x squared minus 4x minus 41 equal to 0. So 41, I think, is prime. I'm never 100% sure with my multiples of 13. It's not divisible by 2 or 3 or 5 or 7. So yeah, I'm pretty sure it's prime, which means I don't think that this can be factored. I still don't think the quadratic formula is the best approach here. When I see an even b value, I know that getting this into a vertex type form to solve by completing the square is going to be easy. So I'm going to try this approach by solving by completing the square. I'm going to do x squared minus 4x. Draw my little square here. There's x squared minus 4x split evenly would be negative 2x and negative 2x. So it's x minus 2 by x minus 2, giving me an addition of 4 to complete my square. So that I can factor that into x minus 2 all squared. And I'll collect on this step as well to get minus 45. Okay. The advantage of solving by completing the square is that now I only have one instance here. And I get the idea that like solving this by factoring isn't really ideal for everyone. Treating this as a complex difference of squares as x minus 2 minus the square root of 45 times x minus 2 plus the square root of 45 is not obvious to everybody. Okay, that's me solving by factoring. Although in calculus and maybe a bit in advanced functions as well, being able to factor first before expanding is very useful. So what if instead we sort of solved this like a linear equation and we undid the addition, undid the exponent, and then undid the subtraction? All we would need to do is remember something, which I'm not crazy about, and that is that there are two numbers that I can think of that when I square them, I get 45. Those numbers are... Thank you. You made me a phone. Thanks, Marty. That's my son. Okay, well, I'll talk when I'm done the video, okay? That's the phone you made for me. Right, where was I? Yeah, if I think about when is the curve y equals x minus 2 all squared at a height of 45, if I visualize it with a graph, I will never forget the two solutions. So I get x minus 2 equals plus or minus the square root of 45. Now, the square root of 45 is an irrational number, but notice that 45 has a perfect square factor. So this is me showing my work by hand, not resorting to a calculator to do this for me. We should understand how and why this works. 45 is 9 times 5. Then the square root of 45 is the square root of 9 times 5. And the square root of 9 times 5 is the square root of 9 multiplied by the square root of 5. Whoops. The square root of 9 is 3. So the square root of 45 is 3 times the square root of 5. I probably could have just added this 2 to both sides a couple of steps before, and I get my solutions. X is 2 plus or minus 3 times the square root of 5. This is actually fine for a conclusion, but you could write them as two different numbers, 2 plus 3 times the square root of 5, or 2 minus 3 times the square root of 5. Now, what this example doesn't illustrate is that often when you solve by completing the square, your radical will already be in lowest terms. In this case, I still had to simplify a little bit, but I guarantee that when we try this question by using the quadratic formula, the simplification will take longer. And when you're expected to show your work by hand, having bigger numbers is going to slow you down. It's not going to be as efficient. So let's try this one by using the quadratic formula with the idea that, oh, it's just easier to substitute into the quadratic formula. X equals the opposite of -4 plus or minus the square root of -4 squared minus 4 times 1 times -41 all over 2 times 1. So I get x equals 4 plus or minus the square root of, what's that, 16. Oh, I thought that was a 4 plus 4 times 41. So like I didn't need to pick up my calculator to do anything here, but doing 4 times 41, well, I guess I can do it's 164, right? 64 all over 2. Now I do 4 plus or minus the, let's see, 16 plus 164 is going to be 180. All right, so look at these two expressions. Here I have the square root of 45. Here I have the square root of 180. 180 is a bigger number. It shouldn't take me too long to find a perfect square factor like 180. Well, I don't know. Let me just do prime factoring. I'm not going to do straightforward prime factorization. I'm going to split it up quickly. 2 times 9. So there I see 9 is a perfect square and I see 4 is a perfect square. That means that 36 was a factor of 180. 4 plus or minus the square root of 36 times the square root of, if I remove 36, I'm just left with 5. See how the prime factor tree is useful there? I didn't know that 180 divided by 36 was 5. Yeah, I probably could have figured out that 180 divided by 5 was 36, but. And then I get 4 plus or minus 6 times the square root of 5 all over 2, which still isn't as simplified as this expression. Students get confused about what they're allowed to divide by here. Treat this as a rational expression, like from the first half of Unit 1, and only divide factors. Whoops. Remove a common factor of 2 from 4 plus 6 somethings. You'll get 2 plus or minus 3 root 5 divided by 2. Those 2's will divide. You'll get x equals 2 plus or minus 3 times root 5. Now, solving by completing the square, I wouldn't say is fast, but I think it's about as long as this right here. And it can be faster in a couple of cases. I know the video is going a little bit long, but I just want to stress one last option here. Like, for some students really don't like completing the square, and that means that they don't like completing the square. But like, if I give you a function where the square has already been completed, please use this approach. Let's say change of directions here. Let's find the x-intercepts. Of f of x equals, let's try like, I don't know, x minus 3 squared minus 5. Visualizing with the sketch, curve moved right 3, down 5, should have 2 x-intercepts. Use that to remind you. I'm not exactly sure what they're supposed to be, but here's f. X-intercepts are the values of x when y is equal to 0, so I'm going to set f of x equal to 0. And now look, if I give you a function that's in vertex form, the square has already been completed for you. So are you going to expand this to get it into standard form so that you can use the quadratic formula? Or are you going to add 5 to both sides? Take the square root of both sides, making sure that you include both solutions? And add 3 to both sides. Right? Once again, you're allowed your own opinion, but if you think that using the quadratic formula is easier than doing this, I think you're wrong. And if you resorted to using the quadratic formula on every single one of these examples, if these 4 questions would be fair to be on a quadratics test, and they should take us a couple of minutes each. If you resort to using the quadratic formula in every single one, then yes, you will be pressed for space and time because you are demonstrating a lack of understanding of important concepts in this course. From here, if I were to try to use the quadratic formula, I would have to do x squared minus 6x plus 9 minus 5 equals 0, which would give me x squared minus 6x plus 4 equals 0, which has solutions x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So here's my numbers getting bigger. 6 plus or minus the square root of 36 minus 16 all over 2. I get x equals 6 plus or minus the square root of 20 all over 2. The square root of 20 is the square root of 4 times the square root of 5. Show that step, please. will convince me that you're doing it by hand. All over 2. And then students that don't want to accidentally divide the wrong things will only divide factors. 3 plus or minus the square root of 5 divided by 2. I divide the 2's and I get x equals 3 plus or minus the square root of 5. And this is why I say no, it's not easier. It's easier, it just takes longer, and your numbers get bigger, and you have more reducing to do. Well, no, that doesn't sound easier. It is easier to memorize a formula. It is easier to not learn something new, sure. But once you learn this new approach, I hope you agree that it's easier. It's more efficient, at least. Okay, efficient solutions. Practice them.